Okay, so once we have the strain, in terms of the stress, you can ask, how do we switch those? So that's kind of where what we do is we take our equations, we just derive those, and we have these relationships between the shear strains. And what we can do is like break these things out. So if you do that, you spend enough time, you can actually create this matrix here, okay, that when you multiply across, you actually get this thing back. Okay, it doesn't seem like it will work, but I have checked it and it does work, so you can feel free to try that out. And you'll get those, these are basically like 6 equations back. So once you have this in matrix form, okay, so now it's easy to invert this thing. And you can invert and now write this in front of the strain. Okay, so this E hat is like an effective, if you actually do this and go through the process of it, you get a lot of kind of messy math, as you can imagine, and we just write this thing as an effective stress here, this E hat. Okay, so that's how you get stress and strain. And there we have it in sort of concise forms, and this is something that you might have recognized before if you've seen like Hooke's law. A lot of times it's given in terms of strain instead of in terms of stress. So there is a demonstration of how you go about doing that. And one of the things here is, was this thing here. It turns out we call that the D matrix. Okay, the D matrix, and we pulled here. We pulled the effective E out, and you're left with something like this. And that allows us. I mean, look how nice. I mean, that's a 6x6 equation. It's really a big pain to write, but using tensor math, we can just write it very short. So these would be bold. I typically write it like a sigma with 2 lines underneath if I'm writing on paper. But here we have sigma is equal to D epsilon, and D is this material matrix. It's a 6x6, and you can see that it's symmetric. Okay, so that's the material matrix. We have Hooke's law. These are critical because what happens is what we do is we solve for this displacement, and you'll see this. This is on exams and different topics in the course. We solve for displacement. We then get strain. We then use some Hooke's law, for example, to get stress. And that's what we're after as engineers. All right, so that's the end of this. There are some special cases of strain displacement, especially in plane stress and plane strain. Have you heard of those? They do have implications on modeling, and as a modeler, we try to think about those cases and use them as much as we can. With the advent of 3D, really high-end, high-performance computing, you have to ask yourself this question less because you're not so much worried about the computational expense. But back in the day, the treating as plane stress or plane strain was like really critical. So I figured we would talk about that really quick, just as a review, and that will be next.